If you've ever done any handyman work, you know that you need to know what tools do what. And in the same sense, when you're building a network environment, you have to know your building blocks. That's the goal of this nugget, is to talk about the key network devices, the key building blocks that we have in our environment. Well, let's start at the ground floor with hubs and switches. Now, hubs are virtually non-existent in today's world. However, understanding that function will not only tell you where we came from, but will really help you appreciate and now understand the function of switches. Essentially, what hubs do is act as a single connection point for all the different devices in our network. In a previous nugget, I believe the last one, I showed you kind of how the wiring in an organization works, where you have all of the devices that go to wall jacks, and all the wall jacks eventually come down to a patch panel, kind of the central point. And then from that patch panel, we plug them into a device like this. We've got our hub connectivity. Now, a hub acts as that's where the name came from, that hub of connectivity, but is really just a single physical layer repeater. Now, when I say physical layer, I'm talking about the OSI model, which is going to be in one of the upcoming nuggets. Essentially, it receives electric signals and generates electric signals. That's all it knows. It has no intelligence. Like, it doesn't understand those electric signals. It doesn't look at individual packets or data that's being sent. It just says, okay, I received electricity on port 1, so I will send that same electricity out port 2, 3, 4, 5, 6, and so on. Now, the fact that it does that really tells you one of the attributes of it: a single collision domain. Now, that's a technical term that simply means how many ports receive an incoming signal. So collision domain means, well, I guess let me revise that statement. A collision domain really defines how many ports can send or receive at the same time. So if you're taking notes, jot that down. Send or receive at the same time. So on a hub, no matter how many ports you have, it's always one. So this could be, what is this, a 24-port hub. It could be a 500-port hub, with 500 ports, and it'll still be one collision domain. That means one device can send or receive at a time. So when this one right here is sending data, first off, what happens? So let's say this guy on the right wants to communicate to this guy on the left. He will send his data, it goes through the cable in the ceiling, hits the port on the hub, and immediately goes out every single port. Again, it doesn't understand the signal, it just regenerates the signal. So this guy gets it, this computer up here gets it, all the devices, including the intended recipient, so the mission is accomplished, right? The data gets there, but every other person also got that data. So question is, what do they do with it? Nothing. They drop it. They ignore it because they look at the computers, which are intelligent, look at the address headers on that data, and they go, oh, this isn't for me. This is for somebody else. Now, keep in mind, we're assuming that all of these computers are smiling computers. But notice, actually, it was accidental, but this works well. Notice that guy. He's kind of got this straight face. What does that mean? He's a disgruntled employee. You can tell he's not smiling. He's not happy to be here. So what is he maybe doing? He may be out to, I'll just say ill gain. So he could actually open a utility called Wireshark. And what Wireshark is it's a free utility. You can run it on your laptop, on your desktop, and it just reports every single bit of data that's being sent or received to your computer. Now, when it's a hub world, that means you not only see the data sent to and from your computer, but you also can see everybody else's data. So you send an email saying, hey, FYI, I was thinking about increasing the salary of Jane to such and such. This guy has Wireshark and knows how to use it. He can take that packet that he receives, put it all back together, and actually see the email that you were sending about Jane. Okay, not good. So not a very secure thing. Also, a single broadcast domain. Again, a technical term that says how far will a broadcast go without being stopped. So if a computer sends a broadcast, where will it go? Well, we can infer that it's one. It's always one. So whenever this guy sends a broadcast, it goes everywhere without being stopped. Okay, so collision domain, broadcast domain, physical layer repeater, and virtually non-existent. And by the way, before we move on to the switch, this is really where that term CSMA CD comes in. Collision detection. Carrier sense multiple access collision detection. That's the rules of Ethernet, the rules of engagement. I mentioned this in a previous nugget. But when a computer is connected to a hub, it's always listening. It's always sensing a signal, trying to say, is anybody else sending? Because I know since this is a single collision domain, that only one device can send or receive at a time. Now, if he doesn't hear somebody sending or receiving, then he will go ahead and send his data into the switch, which goes everywhere. But remember, the bigger and bigger and bigger our network gets, there's more and more chance that there's two computers listening at the same time. So they listen, they sense the signal, they don't hear anything, so they both send data, and there is a collision. Ethernet has collision detection, which in a hub world is a big deal. And on most hubs, I don't know if this little D-Link had it, but they'll usually have a little light on there that says collision. And it'll blink whenever there's a collision on there. And in some environments, you would see it just blinking constantly. What happens is when these guys detect a collision, they actually back off. They wait a random amount of time and resend that. Now, it's got bounds. It's not going to, I'll wait 5 days. No, it's going to be less than a second. But it's going to wait and then resend that data. And usually it's about a 1 in 1,000 chance that it'll collide again. But again, the bigger it gets, the worse our hub networks get because it keeps getting collision, becomes less and less efficient, and so on. Now, one thing I will say, and then I'll leave the hubs behind, I've seen some math problems like this. They go, okay, well, if that's a 100 megabits per second hub, right? And let's just say there's 10 devices attached, then that means you only have 10 megabits per second of effective bandwidth. So these guys will only get 10 megabits per second. That's not true. That is not true. That is assuming that all 10 of those devices are waiting to send and receive at a time. Now, if all of them are constantly waiting to send and receive, then yes, your effective throughput would be 10 megabits per second. But if this guy on the left is the only device that is actually sending or receiving, he gets the full 100 megabits per second, right? So the speed is there. It's just you really have to think, okay, it's a shared bandwidth thing. So if somebody else is sending, we can't send. We have to wait until they're done before we send or kind of jump in the middle of like a blank spot of their conversation. So it does, if multiple devices are trying to send, lower your throughput. Okay, so let's now talk about the modern world, from hub to switch. In a switch world, every single port is a collision domain. Therein is probably the biggest advantage and benefit of moving from a hub to a switch environment. Because if every single port is its own collision domain, now who can remind me what that meant? A collision domain is how many people can send or receive at the same time. And when we're talking about a switch, I'm going to change my statement. Instead of saying send or receive to send and receive. Now who can tell me what difference that means? It is duplex. So, or receive means we're in half duplex, not half. How about half duplex? So in a hub world, these devices are like walkie-talkies. They can only send or receive. They can't do both at the same time. Whereas a switch is a full duplex device, meaning every single device that's attached to there, every single PC, is able to send fully at whatever that bandwidth amount. Let's say this is a gigabit switch. That would be 1,000 megabits per second, while it's receiving fully the amount of bandwidth at 1,000 megabits per second. So, you could make the argument for saying every port can actually do 2,000 megabits per second or 2 gigabytes per second because you can send to 1,000 and receive 1,000 at the same time. But people don't usually think of it that way. Just not how the Ethernet standard is written. So that's a big benefit. So what that means is I could have 5 devices on here that are all sending at the same time at a full 1,000 megabits or gigabit per second bandwidth, and they are not going to reach their maximum, and they're not bothering anyone. Think about the security with this. With a collision domain, when this guy sends some data and says, I want to send it to this device over on the left, the switch is intelligent enough to say, okay, that device on the left, then I will just take that data and forward it through so only that device gets it. That's the intelligence that I'm talking about. We haven't talked about the OSI model. We will. But data link layer intelligence means it can actually see what's called MAC addresses in the Ethernet world. So it's able to say, okay, you're coming from this source and going to that destination. Well, that's only who will get it. Whereas this guy, just a physical device, meaning it'll just broadcast it everywhere. It goes to everybody at every single port. This one is much more intelligent. So switches they change the world. And there is no reason anymore why an environment would not be running a switch. Can I also introduce one more term at this point? It's going to be called an ASIC. Right? Anytime I say a word like intelligent, I just looked at this. That's the wrong tense. One broadcast domain, meaning one broadcast will go everywhere. Okay, but now let's go back here on intelligence. Anytime you say intelligence, that means it has to think, right? And if you think about it, it really does. This device could be sending hundreds of packets every single second. By the way, you'll see PPS, packets per second, that a device can handle. But it's sending hundreds of packets per second to this guy, and every single one of those packets, the switch has to look at and say, where you're going, where you're going, where you're going, well, that's going to take time. That's going to take some intelligence and processing, right? So the question becomes, does that mean that this is a slower device than a hub? The answer is actually, it used to be yes. There is actually a device, and let me bring it right in the middle here, called a bridge. And you'll hear some people still call switches bridges, bridge, D-G-E, bridge, which was a software-based switch. That means that every single packet that came into it, it did have to look at it, run a little program, go, oh, okay, that's where you're going, let me send you over here. And it was a slower device than a hub, because it had to process every single packet. So you would use these things sparingly, not only because they were slower, but they were very expensive to help improve the efficiency of your network. Well, that's where ASICs changed everything. ASIC stands for Application-Specific Integrated Circuitry. Application-Specific Integrated Circuitry. What that means is some very smart person engineered chips on this device that in the hardware, meaning at the speed of electricity, just because of essentially how memory is processed, as fast as electricity can go, these things can process the intelligence that's necessary to handle these packets. So the ASICs, the beauty of them is they allow this guy to be intelligent and yet work just as fast as this guy. Now, it is possible to overrun the ASIC, meaning let's say this is a 48-port switch down at the bottom, and I plug in all 48-port devices, and they're all sending at a 1 gigabit per second rate. Now, I don't know the specs on that specific switch, but let's just say it wasn't meant to handle that. Well, then you would overrun the ASICs, at which point this thing would flip over to the old bridge software processing, and you would just see the whole network go and throttle and all that kind of stuff. But as long as you're using the switch for what it's designed for, you're not going to overrun the ASICs. Right alongside the world of hubs and switches stands this device called a wireless access point. Because right now, the reason I say they're right alongside is we're talking about how devices access the network, right? Switches and hubs, I'll put H/S, is physical connections, like somebody plugs an Ethernet cable, runs it through a wall, and ends up reaching a device and plugging it in, right? Well, long ago, somebody created the wireless access point. And what that does is you actually take one of these devices, plug it into your hub/switch, and then broadcast your network into the air. Now, as other devices, let's say you've got a laptop over here, or an iPhone, or an iPad, or some other kind of tablet device. I just drew a bed at a hotel room. That's meant to be a laptop, right? The laptops have a wireless card inside of them, so they join the wireless signal and actually end up getting translated from the air, landing down into the cable itself, so they end up looking like a device connected via an Ethernet cable. Now, all these wireless access points follow the 802.11 family, meaning 802.11a and B and G. Maybe some of you have heard of these standards. We're now in 802.11n, and essentially, as we move through these different standards, they change not only frequencies, like if you're doing airwaves, I mean, you're using broadcasting, right? So, I mean, seriously, the FCC gets involved with that, and they've said, well, the 2.4 gigahertz band and the 5 gigahertz band will leave unmanaged. What does that mean? That means that if you want to, you can essentially set up your own little broadcasting station on those bands as long as you follow the rules of the FCC and don't, saturate it or destroy it and interfere with other people's stuff. I mean, there's very specific. That's why, let me say, there's technology out there where you can go buy a wireless access point that's like nuclear wireless, right? You kind of push the button, and it's like, boosh, and it spreads a wireless signal, miles and miles. Matter of fact, if you're bored, this is kind of fun. You might go on to Google and search for Pringles can wireless. There's actually schematics out there of how to create a wireless antenna using a Pringles can, like potato chips, where you can blast a wireless signal 5 miles or something like that with a little tin can. So anyway, kind of fun, but we're now into this unmanaged frequency. And the great thing is we don't have to register with the FCC to go set up a wireless network to broadcast essentially a network signal. So you not only between this family change